Okay. Hi everybody. I'm just gonna add to the last video. So I made the last video a few weeks ago, but I'm using Zoom to record this instead of instead of something else I used. And I realized I couldn't screen share last time. So I am just gonna talk about this a little bit, just to add to what I had last time for experiments 1 and 2. So we were talking about recrystallization and melting point, mixed melting point, and so I just wanted to point out, I think I was talking about it, but you probably didn't see a screen, but it's important to be able to do calculations like this. If you see the post-op questions, things like this could be on an exam, like using solubility to determine how much maximum amount of sample that you can dissolve. You could also calculate percent recovery. As you can see here, percent recovery. This is also a really important calculation to do. And you want to make sure to use a solubility at cold temperatures. So this is how much solubility at cold temperatures, and the solubility also in high temperatures. So it's important to know that when you do recrystallization, you start off with however much kind of dissolves, and of this amount, you kind of take it to the next step. So this is under hot temperatures, and then under the cold step. So you want it to dissolve. So you're gonna calculate how much dissolved and how much didn't. You're gonna remove the mass that didn't dissolve, kind of as impurities, and then at cold temperatures you want it to not dissolve. So whatever doesn't dissolve, you calculate. So you take this amount and then you kind of subtract out the amount that didn't dissolve, and here you subtract out the amount that did dissolve. So you want to keep what does dissolve here and what doesn't dissolve here once again. And then here you want to just make sure you don't add too much solvent. You can add more solvent to make sure everything dissolves. Yeah, so like questions like these might be important to note. And then I don't want to make this video very long. And then I'm gonna add to that. So from these post-lab questions for experiment 2, it would be important for you to well, once again, it's recrystallization like experiment 1, so you do want to know what the correct solvent is based on polarities. You match them up. You don't want the exact same polarity as I said in the last video. You want, I kind of call it a one-up rule, so you want to make sure you're a little bit more polar than whatever sol you have. Your solvent is a little more polar. So I think I might have already said this, but I cannot remember. But for instance, something like if you had something with a bunch of bicarbonyls, like I think benzyl. So if you had something like benzyl, I know my drawing's a little poor, but you would use ethanol as your recrystallization solvent because you can match the polarity kind of. It looks like acetone, and then you don't want to use acetone because that's a perfect fit, so you would use ethanol instead. So yeah. So then about here, here you want to make sure you know that how to do the mixed melting point analysis. So that's important. Are solids A and B the same, unknown? So with mixed melting point analysis, you can tell if it's the same, because then you won't see any broadening of your melting point range, and you won't see any lowering, which you would see if it was an impurity. So I think another common mistake here is sometimes I think students think that the solid A is not pure, or the unknown, basically unknown solid, you should assume the unknown solid is pure. It's not impure. Like, it's pure. You just don't know what the identity is. It's like whodunit kind of thing. If you're thinking about like a mystery or something and you're trying to figure out who the suspect is and there's just one. I don't think that's a great analogy, but basically it's pure. It's not impure. It's not a mix of like different components. It's pure. And so you want to just, so if it was A plus like A, you know, if they were the same unknown, then like you wouldn't see any lowering of the melting point or broader range. So just take note of it. But if it were, so if the identity of this was A, then A plus B and A plus C would give you results like broader range and lowering a melting point. And I would say, once again, I would say about you probably want to be within like 1 to 3 degrees. That's pretty close. If it's greater than that, yeah, it can get a little harder. Yeah, so I think that's this question 2 of postdoc question 2 is something important to watch out for. So basically be able to ID an unknown by mixed melting point analysis. I'm gonna talk about experiment 3. I'll just pause the recording right now. So once again, we're focusing on the first aspect of the labs. So you've already done the reactions. This is like basically, I think all the GC and distillation and reactions comprise the online part of this lab. But just to review separation and purification techniques, we're going to talk about extraction, which I would consider in this first realm. Okay, so I'm going to talk about extraction a little bit, and hopefully this will make it a little easier for you to study. This is going to be my second video. I already made my first video a few weeks ago on recrystallization and selective melting point. I also plan to make one on chromatography, so TLC and the column chromatography. But to get started, so I'm looking at page 21 of your manual, so this is on extraction. Read the information. I would say like annotating is a really good idea. It's probably overwhelming because it's a cumulative final, which seems like a lot, even if it's open now. So solid liquid extraction. So if you read it, it says extraction is a technique defined as transferring solute from one solvent to another. So yes, that's kind of the main gist of what extraction is. Oh, great. So you're trying to transfer, you're doing separation of components by you partition them into different phases, and so that you don't have to know all the details about that, but I just want to hit the main points. Yeah, they give Dr. Koppel gives you examples like if you prepare a cup of tea or coffee. Yeah, so you're kind of removing solute from like another phase. Yeah, so we're not doing solid liquid extraction. I don't know why I wrote this up here. We were doing liquid extraction. So the two phases you have are liquids, and essentially what's going on is you use a liquid to separate out solute from another kind of liquid. Yeah, I'm learning more about this in my own chemical engineering classes, but yeah, I don't. So that's the main idea. You have one liquid phase. So maybe this is like your separatory funnel. It's not the best drawing. Let's just say we have liquid A and we have a liquid B, and there are some solutes in the purple that I'm drawing. Whoops, on the bottom. So it doesn't matter if it's on the top or the bottom. I don't really care, just one of them has it. And essentially what's going on is I want to remove that solvent into like the blue one into the green phase. Then you just move it that way. But then you remember that when you're doing the extraction, you had, for instance, 3 compounds you wanted to remove. So just remember that there are other compounds in here. So I'm drawing one in like black, and I'll draw one in, I don't know, rainbow pen. I don't think that works very well. Yeah, and then you have like, let's just say there's blue stuff in here too. So you want to kind of like remove it selectively. So just like we want to move the purple stuff into your kind of thing. Hopefully that helps. So you have a you have liquid phase 1, and you have a liquid phase 2. So that's the gist, and how we separate it is also important. So the main idea of experiment 3, another main idea, is that you are doing an acid-base reaction. So we all know everyone likes acid-base reactions. So you can't just like separate it out as it is. You kind of want to like make it have a greater affinity for the other phase. So that's using acid-base reaction is one way to do that. And so we're talking about 2 immiscible. So the 2 phases have to be immiscible. They can't be like, that's a requirement, because if they're not immiscible, if you put them together, they will mix together and you will get like you would get like some emulsion, or you would get something that's like homogeneous solution, and you don't want that. You want 2 separate layers. And so yeah, so the first requirement is that we use 2 immiscible so you need to use immiscible solvents for 2 phases. And as you learn, one of the liquids is always water. I guess that's and you know water is aqueous. So this is your aqueous phase. And then the other one will be your organic phase. So one liquid is going to be it can be anything. It'll be organic, but like in your lab you use ether, but it could be they give you other examples like hexane. I think you use dichloromethane. That's the one example in the manual. Chloroform. I don't think you would use that in the lab because it like can make you pass out. Ethyl acetate. There's other ones too, but these are some organic solvents you use that are immiscible with water. Okay. And then another thing about organic solvents are most of them are not soluble in water. Once again, we don't want that. And they're usually greater than 6 carbons. As you know, like hydrocarbons and having a lot of like CH groups chains in a sense, like the hydrocarbon chain, like that causes something to be less soluble. So this just means it's less soluble in water and then more non-polar. And so we're separating out, once again with the solutes, we're separating out. So let me keep typing. So for the solute, okay. So the solute, we're separating out. I don't want to make the videos very long, but you can always keep up speed. So the solutes or compounds, whatever analytes that you're separating out are organic. So they're organic compounds, and for instance, you guys use 3-nitrobenzoic acid, 1,4-dimethoxybenzene, and 2-naphthol. So yeah, they're organic, but they also could be basic, acidic, neutral, yeah. Okay, so I'm gonna keep going. Yeah, so you should know how to do flowcharts. I will say that's important, but before I get to that, I want to talk about acid-base reactions a little bit. That will also be important for the chromatography. Okay, so for instance, if you have an acid, let's say I have a generic acid plus a base, what do you get? That's a good question. So usually at office hours, I would say you get an ionic salt. Oh, great. Plus water. So in the case you have this, you get that. But I will give you an example. So for instance, like sodium hydroxide, oh, that's not my acid. There we go. To make it less confusing. So like, let's say we have hydrochloric acid plus sodium hydroxide, a generic base reaction. You get NaCl, right? So Na plus Cl minus. This is ionically bonded. So just note that here is also ionically bonded. And then you get H2O. So these two add together, and then, you know, that's your salt, just table salt. And so, yeah, there's ionic salt and there's water. And then just remember that ionic salts, so this is like, this is soluble in water. Ionic salts are polar, and they are soluble in water. And so we're going to use this special property to separate things out into aqueous phase. If it's insoluble in water, anything that's, so not ionic salt, but anything that's insoluble in water will remain in the other liquid phase, whereas the salt is a greater affinity for aqueous phase, so you'll find it there. Okay. And then just remember that you can do this, or it can have carbon chains on it. So for instance, the example that is given in your manual is you have something that has a carboxylic acid on it, and you have a weak base, bicarbonate. So this is awesome. And then you know this is a strong acid, the pKa. pKa is like 4 or 5 or something. And then this is just a weak base. So what happens is you get you just deprotonate it. So you just get minus, you have Na plus. So make sure you don't connect these two because that's another mistake. Just make sure they're not like covalently bonded or ionic. And then the other thing you would get is water. And here in this case you get CO2 gas. That's why when you shake your separatory funnel, you get you vent it out, and then you're venting out the carbon dioxide gas. Well, actually, your textbook your manual says the hydrogen carbonate, carbonic acid, and then that can dissociate into these. Okay, and then yeah, they give you other examples. Oh, so you want to also look at pKs to be able to do acid-base reactions. I'm not going to talk about that much. Okay, so then just to recap what you did in your experiment, you guys used a flowchart, but so you had let's say, once again going to this diagram, you had two phases, and to determine which phase is on the top and which one's on the bottom, it doesn't matter. Aqueous could be on the top or it could be on the bottom. Organic can be on the top or the bottom. It's one or the other, but how you determine this is by relative densities. I don't know off the top of my head all the densities. You can search that up. But for instance, for examples like ether, ether is less dense than water. So if this were like ether, ether would be up here and water would be down here. Water would be the bottom aqueous layer. But then if you had something like dichloromethane or chloroform, I believe chloroform is more dense. I'm just searching up densities. Okay, so I searched up the densities, as you can see here, and they're in grams per centimeter cubed. You can just find them at room temperature, just Google it as I showed you. And you can see that, for instance, when you're looking at these, you want to compare them to the water. So water is the aqueous phase. And then when you compare them, you see that the highlighted are greater than the density of water. So these highlighted are going to be the bottom phase, and then water is going to be on the top. This just has to do with gravity and how the phases are partitioned. And then you see ether is less dense than water, and then ethyl acetate is less dense. 1.0 makes it easy to compare, and then those would be on the top and water would be on the bottom. So organic layer on the bottom and the aqueous on the top. But then the highlighted is vice versa. Okay, and then after you compare those and figure out which is on top and the bottom, usually this information would be given to you if it were on an exam. So just make sure you pay attention to this because this impacts how you drain out your phase. So the phase you drain out is always going to be the bottom one. And so if you're trying to keep that phase, then you drain it out, then and put it in one container, you drain out. Then you drain out phase one into another container. You can remove that because you don't want that. And then if you wanted the bottom phase, you take that container and just put it back in here, and then you continue your extraction. But if you were trying to get just the phase one, you can just drain out the bottom phase, just remove it, discard it, and then keep the phase on the top. So you kind of want to pay attention to which one is organic, which one's the aqueous layer. Usually you keep it, you keep the stuff in the organic layer and then continue moving on, but it depends on what you're doing. So, okay, so I'm just gonna give an example. So you can jumble, for more practice, you could just pretend you had any different, choose one of these organic solvents and just try your extraction with different compounds. So you could just repeat what you have in the example page 24, or what you did in experiments with your compounds, and then just change your extraction solvent or change your compounds, mix and match a little bit, and that's how a problem could be made. So here, for instance, I have pyridine, I have benzoic acid, and I have phenanthrene. And so first off, you don't have to know the names of the compounds, you want to ID what they are. So here, you want to first off, you should ID if they're acidic or basic or neutral. Are they organic? And so here you see benzoic acid, the name has acid in it. This is acidic. It has a carboxylic acid on it. If you don't even know if it's acid or base, look at the functional groups. Here I can see this OH, this H has a pK about like 4.2, I think is what they give you. So it's very acidic. It's this like low pK that's very acidic. And then here, if you look at the conjugate acid of this, it's high pK. If you added a hydrogen here, and protonated pyridine, then you get like, I don't know, 30 something. But anyhow, this is basic, so I did that. And then this last one is neutral or organic. Usually you will always have an organic compound. In your experiment though, you had 1,4-dimethoxybenzene, you had 2 naphthol and 3 benzoic acid. So you had 2 acids actually. So you could get 2 bases or 2 acids. It doesn't have to be an acid and base, but acid and base makes it easier. The example given with the dichloromethane has the acid and base. So if you had 2 acids or 2 bases, usually the basicity and acidities have to be different. So you would separate off of that. So basically, you could have a strong acid plus a weak acid, and neutral. That's another possibility. Or you could have like a strong base, weak base with neutral. These are other possibilities. You could also have just these. You could have more, like we're using 3 for a simple case, but as you can see, these are dissolved in chloroform. So the first thing is, yeah, once again, I said the first thing, ID, oh man. Okay, ID if acid or base, and if you have multiple acids and base or multiple bases, then strong or weak. I know my handwriting's not that great. And then the second thing you want to do is look at your solvent. This can be any step later, but I'm gonna look at chloroform. What is it with respect to water? Chloroform is highlighted. It has a higher density than water, so it means that this green phase would, like the bottom phase, bottom would be organic. It would be chloroform. Top would be water. It'd be aqueous. For instance, if this was ethyl acetate, then I would say the top is organic and the bottom is aqueous. But I think you get the point. Okay, and then from here you want to go like, okay, so when you have acid or base, it doesn't matter what step you do first. I want to separate out either the acid or base first. I'm going to have to separate out these two because the neutral compound is always going to be, I guess, extracted and left last because it doesn't move. The organic compound will just stay dissolved in your chloroform. It's never going to move to your water phase, while we are trying to move these to the water phase by making it into ionic salt. And then later, just using if it was acid and you use the base to extract it, then you just use acid again to reprotonate it and I guess bring it back to normal in a sense, once after separated. So these are all dissolved in chloroform, and remember chloroform doesn't react in an acid-base reaction, so these are all left as they are in normal state, so it would be protonated here and deprotonated here. So nothing occurs in the the organic phase right now. Okay, so you have two choices here because you have acid or base. When you have a strong acid and a weak acid, or strong base and a weak base, you always have to use the weak one first, because you want to only remove the strong acid. You will use a weak base and only remove the strong acid, because the weak base won't react with a weak acid, and you'll leave the weak acid behind. So you want to use the weak one first. If you had these two possibilities, you always have to use weak first. Then you use strong. So if you had a strong acid and a weak base, weak acid, you use a weak base first to remove the strong acid. Then you use weak acid to remove the, weak base to remove the strong weak. Okay, I got this backwards. So you use the weak base first to remove the strong acid, then you use the strong base to remove the weak acid, and then vice versa, all that. Okay, and then here it doesn't matter. We can use acid or base. So let's say I use acid first and I want to remove so we can just use HCl since it's at our disposal. So then I separate out our layers. And so what's going on is positive is protonated now. You can see here. And then you still have benzoic acid. Adding acid to acid does nothing. And you still have phenanthrene here. And so once you have the acid, acidic conditions, you can see this is protonated. Oh, and also it's a counter ion, so just Cl minus. And the next thing you have to do is make sure you label. So here, okay, so you can tell this is our organic phase, organic layer, or phase thing. And then this is our aqueous. So I guess if I was going to say the steps, the third thing is choose acid or base to remove whatever you need to remove. So like I was talking about here, you have to make your right decision. And then the fourth step, is you label your layers. So you have to label aqueous, aqueous or organic, or top or bottom, and then here this compound is aqueous, but we said chloroform's heavier, so it's top, aqueous top. And then this is organic bottom. And then once you have that, we're going to do the same thing. So this is separated out. What we do to finish this off here is all we need to do is add base again. So let's say we use NaOH. And then what happens is we are back to pyridine. So now this is extracted. And you can use vacuum filtration and then like remove all the solvent, the aqueous solvent, and then get your solid here. Oh, once again, you used solid compounds and you dissolved in here. So now we're getting it back to solid once again. This is liquid extraction. And then we have to do the same process here. So I'm gonna pause the video and you can try it. Okay, so hopefully you got this. So as you can see here, we used a base. We knew another acid-base reaction, so here's our acid, and then here was our base. And so, I'm sorry, that's not our base. So here's our acid, and here's the base, and then we get conjugate base and conjugate acid, which would be just water. As you can see, this H adds to the OH, and you would have water, more water, and this is just aqueous. Your aqueous layer. Oh, also remember the NaOH is dissolved in like water, and so is the it's a NaOH solution and it's a HCl solution, so you have plenty of water, and then you're also making more water because of the acid-base reaction and your conjugate base here being a water and conjugate acid here being water. But anyhow, so you have aqueous, so anytime you do an acid-base reaction, so any of your acids and bases will always be in the aqueous layer. Don't ever say it's in the organic layer. And then this is in the organic. It's kind of boring. This guy has just been moving around, doing nothing in the same phases. And so you have the aqueous top, once again, same thing, based on density. And so aqueous top, aqueous organic bottom. And so here we just add acid to touch up. And so what you get is back to your original benzoic acid. We removed it. And you can do vacuum filtration, remove it to solid. So we got those two. Remember vacuum filtration from the recrystallization. And then here, what you have to do is the last touch-up step. So you basically remove solvent under reduced pressure. And then just remember that's the setup where you make the pressure less by using a vacuum. You have a round bottom, it's your compound. And basically what you are doing is you might heat it a little, but usually you don't need to do that. There's a to vacuum. Okay. And basically you reduce the pressure, and so then it's gonna evaporate more quickly. You just want to speed up the evaporation. And so that's basically what's going on. And then as you do that, you might get viscous oil. And then when you dry it up, you could even get solid. So just remember this setup is different from vacuum filtration. Oh, the reason okay, yeah, so that's what happens. Yep. And then just know how to do this if you had these other possibilities. So this is the first possibility, second, third. Always weak first, then strong. So you could have used weak acid, strong base, if you were removing weak acid and strong acid for bases, and if you had two acids, weak base, strong base. And then also remember the top and bottom labels would be switched if you used something like ether ethyl acetate. Okay, I think I got most of the concepts down. So once again, when you have the reason why you are venting in your experiment is because you do use sodium bicarbonate, and so sodium bicarbonate, which is right here, or like just the bicarbonate itself, you can dissolve it and get water and carbon dioxide, and then in order to keep the funnel from blasting off, that's not a fun experience. I've seen that happen before, and that's so basically to do that you need to vent. So you put like a stopper, then you like shake it. If you see your manual, they describe the whole process, you probably remember, and then you shake it and you vent the carbon dioxide gas towards the back of the funnel. I'm sorry, not back of the funnel, back of the fume hood. Okay, I think, yeah. Oh, I forgot to label. I think it helps for some people. So 5 repertonation, or like depertonating back to original state. After the labeling. And then you also, step 6, you might call it, is like touch up. So are you using vacuum filtration, or are you using removal of solvent? And just note the two are different. Vacuum filtration is just like straining out something, kind of like pasta, if you think about it. And here it's a little different. You're just trying to evaporate the solvent. Okay, yeah, and then another thing I want to, I guess a few things I want to add. So here, removal of solvent under reduced pressure. Basically, what you're doing is reducing the boiling point. So when you make the pressure less, your boiling point goes down. I think that's why if you go on the top of a mountain, you can boil things at lower temperatures. Yeah, so lowering the boiling point so it evaporates just quickly. So or vapor pressure increases. And then just remember to use pKa's, especially here when you're trying to determine what's strong and weak acid, or strong base and weak base. You have to use pKa's. Another thing I'm gonna add is conjugate pairs. I think this is helpful. So strong acids are associated with weak bases. Weak acids are associated with strong bases. So conjugate, I guess, pairs in a sense. And so just note that they will be paired up. Oh, and another thing is when you do the reprotonation in the basic, if you're trying to get it back to acid, like here, or if you do a deprotonation, like to get the base, the protonated base back to a base, what you do here is doing this step just makes it, it will basically recrystallize whatever you have, and then that's why you can do vacuum filtration. You can do like a recrystallization kind of. Like that's why you put in the ice and you vacuum filtrate, so it's not soluble anymore. And then something else to pay attention to is I'm losing my train of thought a little bit. So I'll talk a little about post-lab questions, and also you just should remember that this experiment was a little continued in experiment 4, and also you took melting points of your extracted compounds to see, kind of assess purity, so you can, like, once again, this is a separation technique, and then you can assess the purity using mixed melting point, and like, not mixed melting point analysis, but just looking at your melting points, and then you can see the melting points, how close they are to the pure substance, or how close they are to your mixture of those compounds, their true values. Also know how to do percent recovery of the 3 solids, so you just know the ratios. So if you use 1, 2, 1, or 2, 1, 1, or 3, 1, 4, it doesn't matter. Just know how to use those ratios, and for instance, like page 29 of the manual, be able to do percent recovery calculations based on what distribution you have. And then you took the TLC, your TA took the TLC of each of the extracted compounds in experiment 4, and basically what you were doing is you took your pure components, and then you took all the extracted compounds of 3 of those, and then your mixture, and you did the TLC, and you should have noticed what are the relative like polarities and RF values, and I'll talk more about those like next week, or not next week, in my next video. And okay, so here's experiment 3 post-lab questions. And so something like this, you can get more practice, redo this problem, or like get more practice, so you should be able to ID what these are. Are they acids, are they bases, are they strong, are they weak, are they neutral? So here you can see it's neutral. Usually when you have ketones or just benzene rings, those are like organic or neutral compounds. Here you see an acid, this is immediately like, I know this is an acid, it says acid in the name. Sometimes you can even look at the name, and if it says acid, it's acid. And then here, is this an acid? I don't see any hydrogens I can deprotonate. So, of course, this is a base. So then you're doing an acid-base extraction. And then your example in your manual, like the one you actually did performed in lab, that's where you had you had a strong acid and you had a weak acid, and then you used the strong base, NaOH, and weak base bicarbonate to separate out compounds. But you can also do it with like if you had a weak base and a strong base solid and tried to use acid, strong acid, and a weak acid to separate things out. So maybe you use hydrochloric acid with like acetic acid, which is like weak. And then here it says DBN has 2 nitrogens. Which one's more basic? Which one gets protonated first? And then you want to just make sure when you're doing this, you want to look at like you can't really see the pKa's, but another thing to explain pKa's and is conjugate acid base stability, and so you can look at like resonance. Resonance is actually honestly the big one. Same thing here, kind of look at resonance. And resonance stabilization makes something more stable. So I'm just gonna end this. So if you have resonance, whatever you have, the acid or base is more stable. And more stable means it's weaker. So it's a weaker and less reactive acid or base, and then that means its conjugate is a stronger acid or base, whatever, depending on what you have. So hopefully that helps. And I think, yeah, I think that's all that's to be said. And then, yeah, in the procedure, you did have a sodium sulfate, like drying step, the neutral fraction. The sodium sulfate, I guess I'm gonna talk a little bit about that in the case. It's probably not gonna be tested, so don't worry about it too much. But it's something nice for Orgo too, since you do practical and you also talk about you use sodium sulfate to dry things sometimes. But so sodium sulfate, what it means by drying isn't you lose all your samples, like liquid in the sample. It doesn't mean you remove all the liquid. What it just means is get rid of water. So I'm just getting rid of all my aqueous stuff for like you did that for the organic layer, because all I want is only organic solvent. I don't want any residue like water in it. And so that's what putting sodium sulfate in and then kind of like swirling around and seeing that it it is like free flowing. So when you shake it, it's not like clumped up and it's free flowing. That's something important to know how to do in like organic too. So again, I think that's all I have. I don't know how long this video is, but I apologize if it's really long. You can feel free to skip sections. Yeah, hopefully that helped. This was not one of my favorite labs, but the flowchart, acid-base reactions, and knowing relative densities and conjugate pairs are the main key concepts. I'll talk about TLC and liquid column chromatography next time.